So hello, everyone. My name is Vodeb. I'm a PhD student at the University of Nova Gorica, just here across the border with Slovenia. So today I will be presenting our work on the topic of detecting and characterizing dark matter subhalos with the Cherenkov Telescope Array. For the outline of my talk, I will start with a short introduction to the Cherenkov Telescope Array. Now, probably not needed the introduction to the dark matter subhalos, since we already heard a lot about this. And then also the motivation for the study that we did. And then we will be presenting the subhalo modeling that we use, how we simulate our data, the CTA survey that we implement for our analysis, and then the results for the sensitivity and how we discriminate, how well we could discriminate between different sources in the gamma ray sky. And at the end, of course, also the population study that we did for the population of galactic subhalos. So to start about Cherenkov Telescope Array, we heard a bit about it today. So CTA will be the next generation imaging atmospheric Cherenkov telescope, and it will be detecting gamma rays in the energy range between 20 GeV to 300 EVs. And it will be especially important for gamma ray astronomy and astrophysics because it will be really an improvement on the current generation of imaging atmospheric Cherenkov telescopes. So it will be able to cover the entire sky due to the fact that it will have arrays in the northern and in the southern hemisphere. And it will also significantly improve on the sensitivity of current telescopes of the same type, and boost the detection area. It will also improve the angular resolution and the field of view, which is very important for observing extended sources. And that will enhance the surveying capabilities of this instrument. And basically, key science projects of CTA are the projects that will be having a significant amount of time dedicated, observation time dedicated to their completion. And two of these key science projects are also two large surveys of the sky. So one will be the extragalactic survey. So observing 1/4 of the extragalactic sky with a very good sensitivity. And then also the galactic plane survey, which is a dedicated survey of the entire galactic plane with different exposures in different areas of the galactic plane. So for dark matter subhalos, so we were already talking a lot about this today. So because of the structure formation in the lambda CDM model of the structure formation, we have this kind of a bottom-up principle where we have smaller structures merging together into larger structures. And this gives rise to a halo, a dark matter halo. And in these dark matter halos, there are clumps or like overdensities, which can be called then subhalos. And within those subhalos can be sub-subhalos and so on. So there can be structure within the structure. And then there are some minimally gravitationally bound dark matter halos that would be basically kind of representing the overdensities of dark matter that would most probably not be massive enough to have a baryonic component. So this is kind of motivation for CTA as well. So in the WIMP hypothesis for dark matter particles, we make an assumption that there is a small interaction, small probability for annihilation and decay of dark matter particles into standard model particles. Those would be heavier particles, but they would then decay into more stable standard model particles, such as gamma rays, for example, that would be able to travel large distances without getting significantly absorbed. And we could be detecting indirectly such signal coming from dark matter from the for example, from the parts of the sky where the overdensities of dark matter are significantly high. So it is estimated that subhalos that are, they have masses that are of the order of 10 to the 8 solar masses would not accumulate baryonic component. So that would mean that the astrophysical signal coming from those objects would be very dim, and that would make better prospects for detecting the dark matter signal that would come from those objects. So there has been previous works that have been done on predicting the CTA sensitivity to dark matter subhalos. This was done by Coronado Blasquez in 2021, where they assessed the sensitivity of CTA to different observational scenarios, but mostly to subhalos that would be at higher latitudes. So they were looking at the extragalactic survey that I presented there. So they were mostly looking at how many subhalos could be serendipitously discovered in the extragalactic survey. So now our work is focused on assessing how well we could detect the subhalos using the galactic plane survey. So basically looking at subhalos that would be at much smaller latitudes. So for that, we are applying a similar approach that we applied to our assessment of CTA galactic plane survey sensitivity to pulsar halos, because those are also extended galactic gamma ray sources. And we are applying a similar approach for assessing the sensitivity of dark matter subhalos, considering the galactic plane survey observations. And one of our challenges in this work, because of the very densely populated area that is the galactic plane, we will have to have a very good approach to distinguishing the dark matter subhalos from other known astrophysical sources. So for the modeling that we assume in our analysis, so for the spectral and the spatial model, we are assuming a thermal rim dark matter with mass typically. So for the flux sensitivity at the 1 TeV mass, and then also considering different mass ranges for the dark matter particles, and annihilating for now only in BB bar channel. So we employ the spectral model that is presented in this paper. And for the spatial model, we are assuming just very basic Navarro framed white dark matter profile, and we are using different parametrizations for the scale radii. So one of our main aims is to simulate, kind of to model the whole galactic population of subhalos, and then depending on their properties, assess how many of these halos would be able to be detected with CTA, depending on, of course, different properties, and make the analysis of that. So for that, we're building on top of these two papers that basically do the modeling of the subhalo population in the galaxy, and those are built on the Streffen-Lavalle models. So we are assuming two different models from their paper, which are the fragile and resilient models. So those are basically describing two different scenarios of how resilient are the subhalos to the effects of tidal forces that act on them. So for the fragile model, we would have a subhalo that would basically be tidally stripped for any given subhalo for which the tidal radius is smaller than the scale radius. And this is shown in the plot here. So these are the subhalos that would be left in the population study. This is showing the J factor, and this is the mass of the whole subhalo. And for the resilient, in that case, those would be a lot more resilient to any tidal forces acting on them. So only in case that the the tidal radius is 2 orders of magnitude smaller than the scale radius, only in that case, the subhalo would kind of get disrupted by tidal forces. So our approach that we take is, so CTA, I don't know if I mentioned, but it's probably known that we are not taking real data. So we are simulating the data based on the provided IRF instrument response functions that are provided by the consortium. So we are basically assuming a pointing strategy that assumes a double row pointing pattern. I don't know how well you can distinguish, but there are two rows of pointings over the whole galactic plane, and those will be spaced differently depending on how deep exposure we want to achieve in different regions. So the region that is the most interesting and has the most sources is the inner galactic region. So that region will have the deepest exposure, and then other regions will have lower exposure, but still a very good exposure. So what we do in our analysis, we select 2 places where we position the brightest subhalo from the population. One is in the inner part, so this will be almost very close to the galactic center, and then one is in the outer part where the exposure is much lower, but also considerably lower are the source confusion that we get from other astrophysical sources and other astrophysical signals and backgrounds. Okay, I think I mentioned everything. Okay, so how we do it is we position the source at the sky, and then we simulate the observation of that signal and the observations, and we simulate the signal that we would get, the background that we would get from the instrument. So that is the cosmic ray background, that is the type of background that is impossible to get rid of in the imaging atmospheric Cherenkov telescopes, due to the fact that certain particles like electrons, positrons are indistinguishable from high energy gamma rays. And then in addition to the instrumental background that represents the biggest background of the experiment, we also take into account the interstellar emission model that kind of describes the astrophysical background, so anything coming from the interstellar medium. So to come to the results, so for the flux sensitivity, so these are kind of the models that we are assuming. So we're always assuming a mass of subhalo of 10 to the 8 solar masses, and we are positioning this subhalo at different distances from the observer, and this gives us different J factors and also different extensions. So all of these subhalos will have the same scale radii. And so what we see, and what is also known from experiments, is that the more point-like the source, the better the sensitivity to such a signal, because very point-like sources are easier to distinguish from the diffuse backgrounds that we have in our analysis. So we see here the comparison between the positioning the source at a lot, so basically far away from the galactic center, and positioning it a bit closer to the galactic center. So because the exposure is better in the galactic center, we get slightly better sensitivities. But at the same time, we see that adding or not adding the diffuse emission is maybe slightly more obvious than in the case of location that is very far away from the galactic center. What we also considered was taking the source, so taking the subhalo with 10 to the 8 solar masses and positioning it at 1 kiloparsec, but then varying the scale radius. And we see that these sensitivities are pretty much similar to the sensitivities that we get here for the one kiloparsec case, and they do not vary that significantly here. Okay. So we wanted to assess what is the relation between the mass of the dark matter particles and the annihilation cross section that we can probe. with our approach, and we see that we are, compared to the thermal cross-section, we are still like orders of magnitude below, and the sensitivities that we achieve here are kind of in the same ballpark as other results for the CTA sensitivity to dark matter subhalos. So we are also adding some effects of the systematic uncertainty, although right now there are no benchmark models for systematic uncertainty for the CTA yet. But this is what the effect on the sensitivity would be in case of 1%, 3%, or 10% systematic uncertainty. So how would we discriminate between dark matter subhalos and the known astrophysical sources, which for sure are going to be plenty in the galactic plane? So the analysis that we selected for this was kind of going for, so in our template analysis, we had a dark matter signal with a fixed cross-section value that was in the mock data, and then we fit it with either a dark matter subhalo or some alternative spatial model, which could be either a point source or it could also be an extended Gaussian source. Then we varied the cross-section of for the dark matter annihilation up to the point where the dark matter subhalo model, the fit was significantly better than the fit that we achieved with the alternative spatial model. And these are the results that we see here. So we did the analysis in 3 energy bands. So this would be for the lowest energies, middle energies, and the highest energies. And we see that for the simple detection, that would be simply 5 sigma detection of the subhalo. The worsening of the sensitivity, basically, if we would not be fitting the correct model, so if we would want to discriminate it for a point-like source, is shown with these dashed curves. And then for discrimination from Gaussian radial profile is shown with this, the upper one. I don't know how well they are distinguished here, but so these two are pretty similar. And then we also tested for the discrimination from a generalized Gaussian radial profile. And in this case, the sensitivity would get significantly worse. But then here we can argue that these are preliminary results, and we could argue that there could be a better fit. Maybe we could select better parameters for the generalized Gaussian radial profile that would improve these results. Okay. So one of the things that would help with distinguishing the subhalos from other astrophysical sources would be to be able to reconstruct their angular profile. So basically reconstructing their flux as a function of the distance from the center of the source. And we did the analysis for kind of decomposing the subhalo profile into at least two significant points. Let me see. Yeah, two significant anuli up to 30 parsecs distance from the center of the subhalo. And so the line that shows this is the full line here. So this is the comparison. The full line is the comparison with the lines that were shown in the previous plot. So this would be the simple detection. And we see that we are quite significantly above that. So one of the things that we also tried was, so these are the purple lines, are the modeled profiles of pulsar halos. So those are extended gamma ray emissions around pulsars, recently discovered in HAWK data. And so we wanted to see how well could we distinguish a subhalo from a pulsar halo. And we see that the distinction could be quite efficient, even with only 2 anuli that we used here. So for the population study, as I mentioned, we considered 2 different populations. So one was the resilient model, one was the fragile model, depending on how the subhalos behaved under tidal forces. And so what we did for the population study, we assessed the integrated sensitivity to, we assessed the integrated sensitivity to these benchmarks, some benchmark subhalos from each population, and then we compared the subhalos in the population with the integrated sensitivity needed for detection, and we assess basically the cross section needed for detection of at least one subhalo in the population, and this gives us order of magnitude 10 to the 22 centimeter cube per second for detection of one single brightest subhalo. Maybe I don't have to go through this. So for the conclusions, so the CTA galactic plane survey will discover a lot of extended gamma ray sources, and among those, many will be unidentified, which means that there could be a signal from dark matter subhalos in the detected sources. So our approach quantified how many and under what conditions we could detect these subhalos, and we see that we are pretty much in the same ballpark as the previous results. So comparing with other observational strategies for CTA, and we kind of get to the conclusion that for detecting one subhalo, we would have to reach sigma V of 10 to the minus 22 centimeter per second. That's all. Thank you.